Multiple pipe flow networks are common, particularly in water supply and in sewage networks. These problems are solved by recognizing and exploiting their similarity with electrical networks. Here too, we have pipes in series and in parallel, as we have resistances in series and parallel in electrical networks. For example, we say these three pipes are in series. The first pipe of length L1, diameter D1, roughness epsilon 1. It has a pressure drop or delta P1. Similarly, a second pipe and a third pipe. Just like in the electrical networks, we have here for this series network of pipe, the volume flow rate through one should be same as volume flow rate through the second and should be equal to volume flow rate through third and so on. There is a common volume flow rate, just like there is a common current in three wires connected in series. But the total pressure drop is the sum of the three pressure changes, delta P1 plus delta P2 plus delta P3. Just like the total voltage drop is the voltage drop across the constituent resistances in a series network. Similarly, a parallel network. Here, the total volume Q dot flowing through the system is equal to Q1 dot plus Q2 dot plus Q3 dot, just like currents in a parallel electrical circuit. But the pressure drop through each one is the same. Delta P1 is equal to delta P2 is equal to delta P3. The voltage drop is same in similar electrical networks. Analysis of piping networks, no matter how complex, are driven by two simple rules. The flow rate balance, total volume flow rate into a junction of pipe is equal to the total flow rate away from the junction, because the volume of the flow cannot be created at a junction. Then the pressure drop between two junctions is the same along every path between the junctions and the paths. The paths being parallel to one another. For example, consider a network in which between junctions A and B, there are two paths through pipe 2 and 3 and through pipe 4 and 5. So the above two rules translate into writing that at junction A, that node A, Q1 dot should be equal to Q2 dot plus Q4 dot. The flow coming in through pipe 1 is the flow going through pipe 2 plus the flow going through pipe 4. The net flow at A should be 0. Similarly, at node D, Q4 is equal to Q5 dot. Similarly, at node C and at node B. And then the second condition, that the pressure drop between the two junctions A and B is the same following either path 2 and 3 or 4 and 5. So pressure drop in AC plus pressure drop in CB is equal to pressure drop in AD and pressure drop in DB. We can write pressure drops in terms of the pipe lengths, diameter, and the friction factors for each one of them. Depending upon the complexity of the problem, this could be a handful. Various methods have been developed to solve these equations conveniently, and there are computer calculators available for doing this pipe networks. Let's next do flow through pipes of non-circular sections. The types of forces that regulate the flow through ducts, circular or non-circular, are viscous, pressure, and inertia. We now use a technique where we can relax such state geometrical similarity requirements that has been set out earlier. We use the fact that viscous effects on pipe walls are confined to a thin region very close to the wall, particularly in turbulent flow, while the inertial and pressure forces act over the whole cross section. That is, we are assuming that over bulk of the cross section, the velocity gradients are quite small, and so the viscous stresses are quite small. This allows us to use two different length scales. Up till now, we have used only one length scale, the diameter of the pipe. Now we can use two different length scales, one representing the overall dimension, like the diameter, and the other scale over which the velocity varies near the wall. If we assume this layer of thickness delta, then delta would be a length scale over which the velocity varies, so that the shear stress now can be estimated as mu times the velocity gradient, characteristic velocity gradient, which is v divided by delta, rather than v divided by L as we have been doing previously. The first length scale is the so-called boundary layer thickness delta. The velocity varies from 0 at the wall to the bulk velocity over the length, so that the velocity gradients of our order v divided by delta, this being the thickness delta for non-circular pipes. These shear stresses of order then mu v by delta, and the shear forces are of order mu v by delta, which is the shear stress, times the area over which they act. Now the area over which they act is the perimeter of the pipe times the length of the pipe. P times L is the total area over which these shear stresses act. P is termed the weighted parameter, so that PL represents the area on which the shear stresses act. The corresponding pi number for the shear forces would be F mu delta divided by mu v PL. Earlier, we may not use this artifice. Delta was taken as a L, so that the pi number was F mu divided by mu v diameter. The inertia forces applied to the main flow, F is like mass times acceleration. Mass is like rho times volume. volume is like the cross-sectional area A times the length of the pipe, and acceleration is like v square by L. The resulting pi number is F inertial divided by rho A v square, where A is the cross-sectional area of the pipe. And from this, we get a Reynolds number like pi number. The new estimate of the shear forces, a new estimate of the inertial forces gives you a Reynolds number like pi number, which is rho delta V divided by mu L into A by P. Consider two pipes of the same length carry the same fluid at the same average speed. It stands to reason that the boundary layer in the two pipes would be the same and the flow would be similar if this quantity would be the same in the two pipes. The value of A by P for a circular pipe is pi by 4 d square divided by pi d, which is d by 4. So, we take 4A by P as the equivalent diameter of any pipe. For example, this rectangular pipe with dimensions A and B, area is AB, perimeter is twice A plus B. So, the equivalent diameter of this pipe is 4 times this is called the hydraulic diameter and is represented by d sub h. So, if for non-circular pipe we calculate the hydraulic diameter and then replace this non-circular section pipe with a circular pipe of diameter equal to the hydraulic diameter calculated, then we should get the same pressure drop and the same flow rate. Thus, the pressure drop in a non-circular pipe can be predicted quite well by calculating the pressure drop in a circular pipe of diameter equal to 4A by P. Using this as the diameter D, we can use Moody's chart or the Colebrook formula. In this slide, we have shown the calculation of the hydraulic diameter DH for 4 different shapes. First, a circular diameter pipe in which the hydraulic diameter comes out as the diameter of the pipe itself. For a rectangular pipe, it is twice AB divided by A plus B, was shown in the last slide as well. For an annular pipe, the weighted parameter is pi times d naught plus pi times di, and the area of flow is pi by 4 into d naught square minus di square. In calculating 4A by P, we get the hydraulic diameter as d naught minus di. This technique can also be used for pipes which are not flowing full. In the last picture, we have shown a circular pipe flowing half full. The liquid occupies only 1/2 the area of the pipe. And then we show that for this pipe also, the effective diameter is D. Under these circumstances, the cross-sectional shape of the model may deviate from the prototype as long as the hydraulic radius is scaled in accordance with the length scale factor. The concept of hydraulic diameter is widely used in hydraulics, even in open channels. It permits relaxation of geometric similarity for the cross-section of the flow as long as the flow is turbulent and the boundary layer is laminar. For open channels, the pressure does not change, and the change in non-gravitational pressure P is equal to P plus rho Gz is related to change in elevation. We do an example. Consider a painted steel channel. And we look up the table and find that epsilon is like 2.4 millimeter in such painted steel channels. Determine the slope of the channel required for a flow rate of 6 meter cube per second at a normal depth of 1 meter as shown. So, to treat this as a pipe flow problem, we calculate first the hydraulic radius. The wetted parameter is 1 meter plus 3 meters plus 1 meter, a total of 5 meters. The flow area is 3 meters into 1 meter, and therefore the hydraulic diameter is 4A by P, that is 2.4 meters. This could be treated as a circular pipe of diameter 2.4 meters. A flow rate of 6 meter cube per second gives an average velocity of 2 meters per second. Flow rate divided by the cross-sectional area. Treating this as a pipe flow, we calculate the Reynolds number, which comes out to 4.8 million, and the value of epsilon by d as 0.001. The value of f corresponding to these parameters from the Moody's chart is 0.0197. Actually, I used the Colebrook calculator to determine this value. And the head loss per meter run then is given by HL is equal to F times V square divided by 2G into L by D. And if I plug in all the values, I get a head loss equal to 0.00167 meters. And this head loss is obtained purely as the head loss in elevation, since the pressure is constant, is atmospheric throughout the channel and the velocity is same. So the channel needs to slope 1.67 millimeter per meter run of the channel. There is a well-developed theory of open channel flows where we do not make these approximations. And there is a standard Chassis formula, and if we use that, we would have got a result of 0.016 meters per meter run instead of the present result of 0.017 meters per meter run. So this does instill confidence in the concept of hydraulic diameter. So even though the open channel has a separate theory to deal with, we could model it as a pipe based on the principle of hydraulic diameter and get a result which is well within the range of accepted values. This shows the power of characteristic lengths properly used. We extend this a little further, and we said that in the channel of the previous problem, we now introduce a painted steel barrier in the middle as shown. Just erected a thin barrier in the middle. determine the reduction in flow rate. Now, in the presence of the barrier, the channel splits into two exactly similar channels. Let us calculate flow through one channel. We first determine the hydraulic radius of one channel. The value of wetted parameter is now 3.5 meters. 1 meter plus 1.5 meter plus 1 meter. The flow area is reduced to 1.5 meter into 1 meter, and so the hydraulic diameter is 1.71 meter. Since the slope remains the same, the head loss remains the same at 1.67 millimeters per meter run of the channel. The head loss is related to the velocity head, and the value of friction factor F is obtained. And then we determine the velocity value V. The value of epsilon for the painted steel is 2.4 millimeter as before. So the epsilon by dH is 2.4 millimeter divided by 1.71 meter, which is 0.0014. I go through iteration again and determine the value of V as 1.62 meters per second. The value of F has converged. Thus, the flow velocity through the channel is 1.62 meters per second, and the volume flow rate is 2.43 meter cube per second through one half of the channel, or 4.86 meter cube per second for the whole channel. Thus, the introduction of barrier reduces the volume flow rate by almost 20% because of the additional shear stresses on the central barrier, which reduces the flow velocity. Thank you.